Later on, we are going to go into each fold, and that is going to iterate over the number of epochs. And for every epoch, we are going to first go into this for loop that is going to iterate over the train loader, and it is going to do all the operations to predict and calculate the losses, and then backpropagate that loss and calculate the new weights. And it's also going to take some values for the statistics that are going to be plotted later. And later, we are, in case that we are in the last epoch, we are going to calculate the values for the precision, the recall, and the average precision and recall. And after we are done with the training process in this epoch, we don't want the network to be learning anymore. So we are going to deactivate gradient, and we are set the network to the evaluation mode. And now we are going to iterate our network through the validation loader. And here you can see that we are going to get the predictions and the losses, but we are not going to backpropagate them because we do not need to learn now. We are just getting some statistic values so that we can see during the training process how our network is evolving. We use our list of dictionaries for each fold to add those statistical values that later on we are going to plot, and we print some informational messages. And later on, once the network has fully trained, we store the end time, and we also print how long it took for the model to fully train. And as we can see here, this is the execution of one training process, and it goes all the way up to 100% in the first fold, and then it gives you the validation accuracy and the training accuracy, and we can see that it gives us the accuracies and the losses for each epoch in the process, and then it also tells us the new best model weights have been found, because as we said before, this is the first epoch and the best loss was set to be infinite, so of course this is going to be better than the best previously found. But now we have already set a best loss, and if we find a loss in the validation set that happens to be lower than the previously found, then it will save that model instead because it returns a better loss than the previously found one. So this will be another fold, this will be another fold, and as we can see here, we have found a better loss than the previous one. And as we have set 5 different folds, we have this same process 5 times. And at the end of the training process, we can see that the total time taken to train this model was 1,500 seconds, or about that time. But of course, that will depend on the hardware that you are using. Once we have trained the model, it's time for testing it. First off, we are going to plot the training values obtained previously. We are just going to scroll quickly through them because here we are just going to see the losses and the accuracies for the training and the validation processes that happen in the cross validation for each fold. So we are going to have 5 different plots. Now we are going to calculate some performance metrics on the test dataset, which is thankfully it has not been seen by the network during the training process, so it's going to be a fair comparison of how this network performs against the YOLO one, because it's going to be shown previously unseen data. It is of course from the same dataset, but it is previously unseen data that has not been involved in the training or validation process. So we are also going to be calculating the precision and the recall, and this is a very similar process to how the training loops work. And finally, we get a precision of 61%, a recall of 62%, and an accuracy overall on the tested dataset of 76.62%, which is quite good for this quick PyTorch model. And finally, we are going to show some output images to see how the bounding boxes and the labels look when you input some images to the network. And we can see here a TV monitor, a bird, a train, uh, apparently a dog, but this is supposed to be a sheep. But as we said, no, this model is not perfect. A TV monitor, which is a little bit shifted to the right, so that is an error in the bounding box calculation. But as we can see here, it predicts this aeroplane quite well, this aeroplane here very well as well, this horse here, this train, and this cow in this image. So overall, our PyTorch model performs very well.
Okay, so now I'm gonna explain the YOLO algorithm. What we first do is just define the base path, as we do with the other algorithm, to store the reduced images that are the ones that, the reduced dataset that contains the images which contain only one object, and we just divide them to compare between the two algorithms. Here we define each folder for the reduced dataset, and we put there all the paths. So here later we can get the last 800 paths from the reduced dataset and get from each one of them the image, the labels, and the boxes, bounding boxes of the objects. So now here's where the algorithm is used. All the labels that an object could possibly be are stored in the YOLO version of 3 txt. So we just get them from there and store them in this variable. As the YOLO model is already implemented, we just need to load it with these two files, the weight files and the configuration files. Afterwards, we define this function to get the bounding boxes and the detected classes with an image that we get through the input. And we return the boxes, the confidences of each box, and the classes IDs. And this function is just to draw the boxes in the image. So for each image in the path, we get the boxes, the confidence, and the classes IDs, and as we only have to show one box to compare between the objects, like between this algorithm and the algorithm we implemented from scratch, so we can see how the other works in relation to the YOLO algorithm that's basically really good. We just get the predicted label based on the box that we get the maximum confidence from, and we just compute all the metrics, and we print only the last 15 images. And I'm not gonna delve into the results as much because afterwards my colleague Alejandro is gonna explain them. So I'm just gonna explain what we do next. And that's that. Basically, for the images that contain several objects, we're gonna run the model for the last 100 of them, and we do the same. We get the paths and we get the labels and the bounding boxes, and afterwards we just run the algorithm for all the images in that path. And this is just to show that in fact the YOLO algorithm the YOLO model can actually recognize like several objects in each image in comparison to our algorithm, which can only detect like one per image. And that's all about the code. So now my colleague Alejandro is going to explain the results we get from the YOLO model and compare them to what we got in our algorithm. Thank you.
Okay, so hello, my name is Alejandro, and now, as my colleague Luna said, I'm going to talk about the results of the YOLO model. Uh, I'm going to talk of the part of the reduced dataset. and we use this model with the last 800 images. So, um, but finally, we only saw the last 15 images that we trained with this model, and what we saw is the image with the bounding box and some metrics like the accuracy, confusion matrix, precision, and recall. And the first idea was to do an average of these metrics, like do an average for the 800 metrics of the and results of the accuracy, and the same for the precision and recall. But doing some testing of the code and the model, we saw that these results are always the same. One for precision, one for accuracy, one for precision recall. Oh, okay, first we can see that the maths that we can say is doing okay, so the result is being good because we can see here bicycle and it says bicycle, here sheep and we can see sheep, here car and we can see car, okay, airplane. But if you can see the result of the accuracy, precision recall of all of them, there are one for all of them. We only print the 15, the last 15, but it does the same for the 800. So, well, what we think of that? That this is that this model is a very good model, a professional model, and it's in a constant evolution, and it's so good now and so perfect, and we provide the labels that we're gonna use for the images that we're gonna use, so it's not gonna have a bad accuracy or a bad precision or recall. It's gonna not have a bad metrics, and it's gonna have like perfect ones, like a 100% of accuracy, precision, recall. So this is why we don't do an average, because it's gonna be 1 or 100 for all of them. So because this model is doing a perfect job for this data set with the levels that we provide. So now, before, sorry, after see these results, I'm gonna do a briefly conclusion. And we see this model and we see the one that we do by our own. What we can say and what we can conclude is that um, the evidence supports the notion that the continuously improving effectiveness of the pre-trained algorithms, especially in our case, the PyTorch framework, is taking object detections to new heights. So this says that in the future they will gonna be better, and we will have a better results, and we could do better things and better models of object detections or different things. But the thing is that the models that already exist, like YOLO, are better, and they're gonna have better results than the ones that we did by our own. Even that mm, this one, it has a very good results and very good metrics. The accuracy is so good, but this is the reality that we have. This one is better, has better the results, but in the future they will be better because now they are so good, and we are so happy of the results that we have with the one that we do for our own. So this is the conclusion that we can say, and this is everything from our mini project and from the for this presentation. Hope you enjoy, and thank you for your attention.